Haven't you ever wondered what the difference was between centripetal force and centrifugal force? Well, it turns out that centripetal force, that's actually the force that's going to be turning you when you're going in a rotational, like in a circle. But centrifugal force is the force, like kind of, it's the feeling that of your momentum continuing. It's your previous momentum continuing. You have kind of a weird feeling of that moving forward, but you're actually being changed by this. Your forward momentum is being twisted by this centripetal force. We can kind of represent that in a circle like this. Um, Here is the velocity vector moving forward here, and in order to get that to spin around in a circle, we have to apply the centripetal force right here, Fc, and we can visualize that by maybe drawing it over here and combining these two vectors like this. And then we can see how they add up to this one right here in the middle. And that's obviously going to be pushed over here into the side of a little circle. Bam! Right there. And naturally, it's going to require another centripetal force right there. These are going to be perpendicular to the velocity right here. Alright? So the velocity is just turning over time as the centripetal force is being applied and it's twisting these things. So you could think of it like flowers, like petals on a flower. Because they're kind of going to make another here. Let's draw another one here, so you can kind of see this, and let's apply the same centripetal force right there, and that's going to be that one, as you can see, and I'll put that one right here, and that's going to be the new velocity vector over here. This one. Damn, and as you can see, they kind of look like little flower petals or something like that, you know? It's kind of cool. So the centrifugal force, or what the F is centrifugal force? We don't even know what that is really. But anyway, so now let's try to represent these with equations maybe. So I guess the first equation that makes sense to look at is the velocity equation. So the V tangential is equal to ds over dt. Well, what is ds? Well, I guess if we were to draw this little piece of pie here, call this theta, and call this s and that r, then as we know, s equals r theta. This is basically how you can get arc length. Arc length is just a small little piece of the puzzle. And so as you start to change the arc length there, well, there's a velocity associated with that. Obviously, this is like dx over dt. Cool. So this can perhaps be simplified. If you need to use simpler equations, I always like to have this equal to the delta, the time, or so let's say the final, let's say SF, S minus F0 or something like this, over, T minus T0, that kind of stuff. So that way you can just have this at your disposal if you need to remember that. And then you also have RW here at the end. I suppose I could use the pen. So now we have W. What is W? Good lord. W is going to be, I suppose that we could represent that over here. That's going to just be the d theta over dt. So a lot of changing happening here. Well, the velocity is the change of the distance here, which is the change of the arc length. And the omega here, this is angular velocity. That's going to be how fast the angle changes. So both of them are kind of important. But this is a change of angle, and that is the change of distance. They're literally almost the same thing. That's the change of this, and that's the change of this. Interesting. So that's kind of cool. Anyway, the point is that we can again do this with the delta W over the delta time here. And then we can have this equal to perhaps 2 pi over t. Basically, if this was 2 pi, it would take that certain amount of time, that certain speed, to finish that 2 pi. Kind of interesting stuff. Just some various ways to represent these things. We also have angular acceleration. Angular acceleration. I'll be over here. You can represent that as dw over dt. It's pretty obvious. So, yeah, no big surprises there. Let's continue on to perhaps a little bit more of the centripetal force that we have to deal with. Because remember that Fc is supposed to be equal to ma, right? But let's not be too hasty. Let's start with the m, but instead of the a, let's use let's represent a as v squared over r. That's basically like if you were to do like the derivative of tangential velocity and plugging in a whole bunch of letters and stuff and doing a whole bunch of math, and then all of a sudden you would get the v squared over r formula over here for the centripetal force. That's quite interesting. Centripetal. That's it right there. That's the force that's really pulling us towards this center here, that's changing this velocity vector. And, well, from there we can perhaps rewrite this w. Let's rewrite w as v over r. So that way it's going to work with all this. These are sort of separate ideas. This is going to be dealing with the angles and stuff, and this is going to be dealing with like the velocity and the radius, since there's no angles in this particular part. So that's why we're translating these. And then here we can have another way to represent our time is going to be equal to 2 pi r over v. These are just some different equations to represent these variables and concepts and ideas. It's always just really good to have an equation sheet so that you can refer back to all these variables. Another interesting thing we can do with these vectors over here is use the Pythagorean theorem. So notice that we have something called the tangential component, which is going to be this factor right here. And then we can say, hey, well, it's either going to be a velocity or acceleration or a force that's going to be in that tangential direction. I'll use A. So tangential acceleration. Well, tangential acceleration is just d of the tangential velocity over dt, and that's equal to delta v. I guess I'm making this a little bit too small. Don't have to worry about the delta vt on this, but just go ahead and put r and then alpha, and that's going to be over here angular acceleration. So that's going to be tangential acceleration. And then what about the centripetal acceleration? It's going to be this one. Centripetal acceleration, AC. That's actually just going to be equal to vt squared over r, which is rw squared. Interesting how these two things are kind of similar. And then finally, we also have the linear, which is this one, linear acceleration. And it turns out that if we use the Pythagorean theorem here, we're going to go a squared plus b squared equals c squared. So at squared, at squared, and then plus ac squared, and that's just going to be equal to al, this is an l, squared. That's just the Pythagorean theorem right there. So those are kind of the three components that we have that we can relate to them in Pythagorean theorem form in all sorts of different ways. And it's quite interesting. Another important thing that you might need in all this is going to be some conversions. So let's say maybe 90 degrees equals pi over 180 radians, or more importantly, if you have revolutions per minute, you can multiply that by 2 pi radians over 60 seconds, and that will give you radians over seconds, which is what W is always given in. And so if you're trying to convert those two back and forth, that works. We also have revolutions equals 2 pi radians, so just in case you need some conversions, that can help a little bit there. So we have a whole bunch of different concepts that we've learned so far. This will really help with being able to tackle angular momentum or rotational kinematics. Those kinds of videos are going to be coming up. So if this was interesting, make sure to like and subscribe so you'll be updated for those videos. Thanks for watching.